Thank you, everyone, for attending this session. Welcome to A Sound Approach to Concrete. My name is Daniel Butko, and I am excited to share some acoustical research. Thank you, Marcy, Elise, Chad, everyone from TAD and ACSA for this honor. Jeannie Gang's quote here is applicable to the good ideas which come from and are sharpened by partnerships with industry, colleagues, and students who have collaborated on those ideas over the years. In addition to the University of Oklahoma, thank you to several organizations, offices, and supporters, some of which are noted here. Other than incorporating acoustics into design studios and materials and systems courses I teach, I also introduced an undergrad and grad elective titled The Sound of Shaped Space at OU over a decade ago. This course has also fostered continued acoustic research over the years, including some of the content in this presentation. Student accomplishments have been recognized by the Acoustical Society of America, the AIA, and other organizations. As designers and architects, we have access to various codes and guidelines which help produce healthy and supportive aural environments. At its most basic, sound is typically wanted and noise is not. Architectural acoustics deals primarily with two aspects of sound and noise: the exterior or external isolation between spaces, and the interior or internal room acoustics of how sound and noise interact with the shape, the layers of materials, and the impact on the occupants. As frequencies of sound and noise interact with wall and floor assemblies, they can be reflected, either specular or diffuse, and then absorbed or transmitted into or through those layers of materials. The aural environment has a direct impact on human perception, emotion, health, productivity, etc. Various statistics relate occupant behavior and health to acoustical properties. Sound. It's not just the air vibrating, sound means feelings. It refreshes our minds, soothes our hearts, it can make us happy or sad or excited. It also is essential to the communication of ideas and the exchange of information. It's vital to daily life. That's my version of a simple yet profound statement that's used as an anechoic recording in virtual environments, modeled in E software, to generate spoken simulations or what are known as oralizations of design concepts. Being able to comprehend speech is typically related to the intrinsic link among reverberation time, that persistence of sound after the initial source, the speech transmission index, and the clarity of the source within the first 50 milliseconds for speech, 80 milliseconds for music. Here we see a few examples of spatial volume, room shape, and surface articulation. Those faceted, layered, and perforated materials define much of the acoustical character. And a few examples of anechoic chambers which utilize wedge shapes to help diffuse and absorb most sound. Wallace Sabine and students deciphered the relationship between room volume and surface area over 120 years ago. The denominator here consists of each material area multiplied by its measured absorption coefficients or the average noise reduction coefficient. An NRC close to zero is primarily reflective, while approaching 1 and sometimes exceeding 1 due to mounting techniques is absorbent. Current research and the main topic of this presentation began in the spring 2017 acoustics elective and rolled over in what we called the Summer Sound Lab and various other phases of data collection and prototype development in the years that followed. Student researchers and I evaluated spaces for common acoustical deficiencies, which identified a gallery space as a place-based physical sound laboratory for collecting measurements and developing initial concepts. The team analyzed the space and surrounding enclosures using equipment calibrated to collect quantifiable acoustical data per ASTM standards. Recycled denim blankets were also used to define a more absorbent control and develop accurate virtual models in E software. Occupants report discomfort and confusion related to acoustical issues in the space, primarily a lack of comprehension based on the acoustically reflective materials and spatial volume, producing high RT, low STI, and low C50. The measurements also demonstrated low noise isolation class or NIC values, which are similar to a field or apparent STC test for wall and floor assemblies, also causing noise criteria NC to exceed published recommended limits. Literature reviews and experimentation led the team to begin exploring concrete for its potential as an acoustical material. The recipe and shape can complement density to provide reflection, diffusion, and absorption of sound waves. Concrete samples containing variations of numerous additives such as flax, silicon oil, nacre, crumb rubber, vegetable fibers, pumice powder, walnut shells, and aluminum powder were developed and tested. The cylinders were cut into 1-inch pucks and combined with other samples from industry partners for separate ISO impedance tube acoustic tests to determine NRC values. The results showed weight differences along with variations in porosity, shape, and size. The team continued with concrete mix designs of various percentages of aluminum powder and both white and gray type 1-2 cement due to particle size affecting the reaction time and subsequent surface and interior porosity. The aluminum reacts with the cement to create hydrogen gas bubbles during hydration. Sound is absorbed through friction as it navigates through the pores. Evaluating sound wave interactions and experimentation with material science yielded data-driven designed panel concepts. Material and form directly connect to acoustical requirements while being feasible for addressing deficiencies in spoken word comprehension. The team worked with industry partners to fabricate custom concrete panels with nominal dimensions of 20 inches by 20 inches by 6 inches and mean weight of 94 pounds. The collaboration also led to additional conversations to consider integrating the shape and porosity used in the prototypes into large-scale optimized precast concrete panels and planks usable in various project types. Here's an example of the form being stripped from the panel. The concrete experimentation yielded prototype concepts with a working name Adilac, acoustically diffuse and absorbent lightweight aerated concrete. Riverbank Acoustical Laboratories in Geneva, Illinois performed 3 reverberant chamber tests, which emulated potential installation methods as suspended panels, banners, and/or wall or ceiling surfaces. The 3 tests resulted in NRC and equivalent or apparent values due to the space between some of the panels of 0.3, 0.4, and 0.2. There were notable increases in specific frequencies when comparing the results of tests 2 and 3 to test 1 as the control. Aside from the spikes in test 2, test 3 added an increase of 99.7% Sabins of absorption at 125 Hertz, which helps in rooms requiring extensive low-end absorption. Comparing results from the reverberant chamber tests and the impedance tube test revealed the translation between material and form. When compared to the existing empty room data, the prototypical panels produced upward trajectories in all associated acoustic criteria through both hypothetical oralizations and graphed numerical data. The various Adilac configurations decreased the reverb time by 34.9 to 68.1%, with viable options in the low-mid 1 second range necessary for less reverberant scenarios in multi-use spaces. So here's an anechoic recording of that statement I mentioned a few minutes ago.
Sound. It's not just the air vibrating. Sound means feelings.
And then using that same recording as an oralization in the existing empty space.
Sound. It's not just the air vibrating. Sound means feelings.
And then using an Adilac configuration with that same recording.
Sound. It's not just the air vibrating. Sound means feelings.
The compiled data indicates replacing 20 to 37% of a room's surface area with the aerated faceted concrete panels, or suspended in the space, will yield a 40 to 55% reduction in RT at speech frequencies. Data collected on the various concrete pucks and subsequent calculations suggest for every additional 10% of voids per volume, the average NRC values focused on speech frequencies increased by 0.0575 within the concrete mix. When accounting for the panels and sawtooth facets, the total NRC increase is approximately 0.07 per the same 10% voids, with noted heightened absorption in specific frequencies due to panel orientation. Future research includes utilizing aluminum powder with more recycled content, substituting some cement for fly ash, which might result in undesired smaller pore sizes and heat-induced internal sulfate attack when concrete is subjected to high temperatures at the early stage, especially with fly ash, which typically contains additional aluminum. Thank you everyone for attending this session, and I wish everyone an acoustically sound day.